Zoom makes everything more complicated.
Yeah. I don't know if people can see me, but I'm Joanna Scharf, and with Dorothy Dempster, we organized this talk and invited Lisa Donor to give this presentation. Lisa Donor is a professor of environmental studies at Plymouth State University in New Hampshire, and she's been working with in the environmental studies field for 35 years. Am I correct about that? So she's here to give this talk. We had a previous talk on this subject back in July, and this is a follow-up geared more toward a general audience, and also has the, she will talk about results from their field studies that they've been doing since July. All right, Lisa, thank you.
And I just realized I should have stopped sharing so people could see you. This is what I look like. I'm going to stop showing you my face now, but just some guidelines. Feel free to ask questions at any time. I don't mind being interrupted if you don't know a word I used, if I'm speaking too fast, if I've glossed over something you're really wondering about, just raise your hand or type something in the chat. I'm very happy to have that work. And I would just ask that you mute yourselves until you have something to ask. And what else? I guess that's it.
Is the recording running?
Yeah, we're recording.
Okay.
Yep. Okay, so I'm going to share the screen now. And all right, so for the last 2 years, I've been involved in a climate mitigation project that was created by Ye Tao, Dr. Ye Tao, while he was at the Roland Institute at Harvard. And he kind of recruited a lot of people of many different disciplines to help him get an initiative going called MIR, which was Mirrors for Earth's Energy Rebalancing, MEER. Kind of an awkward acronym, I thought. But the idea was to start dealing with climate change by doing something now, as fast as possible. He felt a great urgency for this because of concerning reports coming out of the International Panel for Climate Change, the IPCC. They produce a global report every 4 years. It's comprised of 200, 300, 400 scientists around the world in different specialties. They write up their own section. They do an analysis of how things are changing around the globe, specifically related to climate. And these are meant for dissemination to the public and to government officials. There's a governmental summary in every one of those. So the 2018 summary was pretty alarming. And then the 2022 summary, they started giving early reports of that in 2021. And that was even more alarming. And so Dr. Tao stopped the work that he was doing on a nano microscope, which is what he was hired by Harvard to do. That was his research area. And he started working on climate mitigation and recruited an international cohort of volunteers. And I became interested in that because I teach climate change. I study climate change. My master's degree and my PhD degree were specifically about climate change, but not about modern climate change. I was studying past climate change. And because when I started my research, that was where the big questions were. You know, we have weather stations to tell us what's happening now, but we didn't really know how fast climate could change in the past, how it responded to changes in things like deforestation or changes in sea level. So that's where my emphasis was. But by the time I got the job at Plymouth State University in New Hampshire in 2014, a lot of the emphasis had really shifted to better understanding modern climate. And so I applied all of my research skills to comparing what we know about the past to what we see about now and possible trends towards the future. So that's kind of where I'm coming to this from. The project, the MIR project, when it became part of my research, I had separate funding. And so in order to honor the MIR idea, but to give it an independent identity, I called it MIR CAP, which was really about taking mitigation efforts for climate change and using them to cap or slow down the progress of climate. Not to reverse it and not to totally halt it, but to sort of put a temporary slowdown on it. So my partners on this include a number of other people in New Hampshire. Dr. Eric Hoffman is a meteorology professor. Dr. Sarah Turtle is a biology professor. Dr. Jessica Morton is a chemistry professor. And then I'm in environmental science, but I'm really a geologist. So we're very, very interdisciplinary in our approach to thinking about this as a solution and also problem solving. We brought a lot of different skills to this. And we work with Keene University in New Hampshire, New Hampshire Technical Institute, which is a community college in Concord, New Hampshire, and then Plymouth State University, and that's sort of the New Hampshire cohort of this. A lot of the progress I've been able to make on this has been funded by NSF through a supplemental grant to a project I had called GeoPaths. GeoPaths is NSF's initiative to get more geologists graduated, more students who are not in geology programs, like environmental science, thinking about them as able to get a job in the geosciences through their skills. So that was what GeoPaths was, and we incorporated the MIR project into that. There's another chat here, let me see. How many people are attending live? 1, 2, 3, 4, 5, 6, 7. Good question. This might take me, there we go. All right, so the first logo, I'll go back a little bit. This logo is actually supposed to represent the Earth and the sunlight that's coming to the Earth as the Earth rotates around. We all know we have night and day patterns. When we have daytime, that side of the Earth that's experiencing daytime is facing the sun, and the side that's in the shadow isn't receiving any sunlight. So in thinking about how sunlight affects the globe, it's only affecting half the globe at any one time. And according to your latitude, it's affecting those latitudes differently. We all know that the equator gets more intense sunlight than Vermont, especially in the winter time. But we still get sunlight, it's just at a sharper angle, or a lower angle. And so depending on the angle coming in, when you reflect light off of a surface, it bounces off at the same angle away. A bit like playing pool. If you hit a ball on the side, it's going to dance off to the side. If you hit it directly on, it's going to follow the path of the cue ball. Okay, so this cartoon is meant to show sunlight coming in and then being reflected away. And the idea here that's very important to understand is that sunlight coming to Earth doesn't all stay on Earth. A lot of it is reflected away. If you are on the International Space Station looking down at Earth, the Earth is shiny. It glows. Just like the moon glows to us when it's receiving sunlight. The light reflecting off the moon is bouncing off the moon and coming to us. So not all the light that comes to Earth stays on Earth. And that's a really, really important factor in understanding this, because most people assume once light heats the Earth, it becomes heat. And once it becomes heat, then it's part of the global warming thing. but light doesn't become heat until it's absorbed. So everything that's shiny is reflecting light away. And if you think about it, the only time that you feel heat from the sun is when you're out there and your skin is absorbing the light. If you are, say, near a, I don't know, near a glass building or something like that, and the sun is hitting it, and then you're getting the light, it hurts your eyes because it's bright, but you're not getting heat off of it, okay? So this is I think, probably the fundamental principle that is necessary to understand why mirrors and this project that I'm going to describe to you works for climate change. All right, so we had some students working with us this summer, and they were excited about creating a logo. So after working on the mirror project all summer, this is the logo that they created. And I thought it was useful because their perspective is that you've got the mirror fighting this fierce sun, right? And the earth is like protected by these mirrors. It's a more fun message, I thought, than ours. All right, so the reason we need to do something. We have increasing amounts of greenhouse gas emissions. These are mostly CO2 and methane. These greenhouse gases are naturally occurring on Earth, but people's activities generate more than is natural. And so the more people on Earth, the more greenhouse gases are being put into the atmosphere. So we know we've increased the concentration of greenhouse gases. We can measure it directly. And the way they do this is at places like the Mauna Loa Observatory, they actually have a little, what they call it, a sniffer. It's just a tower that sticks up above the island, from the top of the island, and it captures air and then seals it off, and they run it through their machines, and they can measure the proportion of carbon dioxide and methane compared to oxygen or nitrogen. And so they know that every single year since they started taking those measurements in 1959, our gases have increased, and it's been a very regular increase. So this chart here on the left is showing you the gigatons of greenhouse gases represented as a measure of CO2 in 2000, and in 2020 you can see the increase, and then everything beyond today's date, 2022, 2023, is a straight line because it's a projection. It's an estimate of what's likely to happen given the trend of population, the trend of greenhouse gas controls, and a number of other things that go into this. This is a scenario created by the IPCC. It's actually an interactive tool, and if you want to play around with it, it's a free download. It's actually very enlightening to play around with. It's called C-Roads. I have the address here at the bottom. You just have to put in C-Roads and in your search bar, and it'll come up. But the point is that, as greenhouse gases increase, so does global temperature. And global temperature is an average. It is measured directly from all of the Met stations. So when you hear your weather report on the radio or the TV in the morning or your iPod or wherever you're getting it, that's coming to you from your local weather service, and that local weather service reports to the National Weather Service, and that National Weather Service reports to a global weather service. And all of the stations all over the world send their data, and it gets combined. And every single one of those stations, like the Vermont station, I don't know, I think there's one in Burlington as the regional station, but every single town has their own weather station, or many of them do. They take their data and they average their data over a day or over an hour or over a month. It depends on the kind of data that they want. But ultimately, the average annual temperature from any one station gets added into this compilation around the globe, And then the average data from each station gets averaged, and that's the global temperature, which is about 57 degrees, by the way. The average temperature of the world is 57 degrees Fahrenheit. And the concern is that that temperature is going up, and it's gone up already by about 3 degrees, 3.5 degrees or so in Fahrenheit. It is projected to go up as high as 6 degrees within the next 30 years. Because there's more people on Earth and there's more greenhouse gases being emitted, and we're not pulling those extra ones out. Okay, so climate mitigation is kind of about managing that. So on the chart on the right, it's showing the degrees Celsius above average, so above that normal amount. And you know, we see it, that we're pretty close to, oh, I don't, it's not showing, oh, here it is, all right. The lower dotted line here is what most people who deal with climate consider kind of, okay, that's our normal range. That's what we think of as a safe amount of change, where, you know, we're not going to experience some sort of tipping point or some sort of threshold where permanent damage occurs. But beyond that safe range is the high risk range. And the high risk range is a range of temperature increase that is going to start affecting our food supply. It's going to affect the circulation patterns in the ocean. It's going to affect storm patterns in the atmosphere. How many of you have been paying attention to California the last couple of weeks? Right? They've had torrential amounts of rain. So they had decades of drought. And now, in like 2 or 3 weeks, they have like received all of that deficit. But the problem is it doesn't take them out of drought, because all of that, if it comes too fast, it doesn't go straight into the ground. It runs off the ground and goes straight into the ocean. So most of the rain that they've received isn't soaking into the soils. It's not soaking back into the aquifers. It is, some of it's being retained by reservoirs, but California's regulations are set up to avoid flooding. And so they're supposed to let out winter precipitation, not save it all. And so the reservoirs are actually still spilling water in order to keep at their winter levels, even though they ideally should be allowed to overfill in anticipation of drought continuing. Anyway, this is just an example of a high risk range. You know, if California experienced this kind of extreme precipitation every year, that would be an example of high risk. High risk in New Hampshire might be the onset of a wildfire season. We don't really have a or New England. We don't have a wildfire season exactly. You know, anybody that works with emergency services know that periodically there are brush fires. Sometimes there's campfires that get out of control. Very rarely there's maybe a lightning strike fire that gets a wildland fire going. That's pretty rare, but it didn't used to be rare. It used to be much more common. And so something that might create us, or put a high risk for New England, would be an increased intensity of fires or an increased intensity of drought. We're pretty well adapted to winter, so increased intensity of winter storms isn't a big deal. We're also pretty well adapted to flooding. That's a pretty common thing that has been a hazard for centuries in our area. But how many of you have air conditioning at home? About half the audience here raise their hands. I don't. I would say probably half of any population in New England does not have air conditioning at home. But one of the likelihoods of, you know, this increased temperature trend, say, is within the next 10 or 20 years, we're likely to start having 20 or 30 days over 90 degrees. and it's not going to be a dry heat. Okay, so that's the high risk range. The devastating range is when we get above 2 degrees Celsius, so that's about 3.9 more degrees Fahrenheit of warming. And you know, the line here that you see, the blue line with the black center, that's the projection if we don't make any changes. If we do what's called business as usual as a world, as a society, that's the projection. So we're projected to go into the devastating range by 2050. Okay, now a lot of these climate summits, a lot of these political gatherings about climate change are to try and change that trend so that we don't experience devastating climate. We're not anywhere near there yet. We're barely into touching the top of the safe range. Okay, and already I think enough of us have experienced changes in climate that are concerning, but we're still in the safe range. The idea is to get us change the greenhouse gas content of the atmosphere, the emissions, so that we get way out of the dangerous range or the high risk range. So part of this tool, the C-ROADS tool, lets you play around with, well, what if? What if I do this? What if everybody around the world cooperated suddenly and we could do, you know, these things that we think are important? So I set up this scenario here to say, okay, all the developed nations are going to peak their emissions in 2030. That means that the growth of emissions, greenhouse gas emissions coming off of all the developed nations are going to be at their maximum in 2030, and then they're going to be less thereafter. And they're going to decrease by 5% every year after that, steadily. Plus, we're going to prevent all deforestation. 100% of deforestation will stop, and reforestation or afforestation, the regrowth of forests, will also take 100% advantage of all the available land that is open to forest growth and reforest it. So this is a very unlikely scenario in terms of what's happening with the forests. But you can see that with that scenario, greenhouse gases drop right back to the 1959 levels by 2100. Okay, so in the next 75 years or so, we get back to where we were. But the temperature response doesn't go back to where we were. And that's because CO2 stays in the atmosphere for a very long time. Once you heat the oceans, that heat takes a very long time to sort of be lost back in outer space. The Earth is a pretty good insulator. It retains a lot of its heat. And so because we're heating it now, it's just like if you heat a pot on the stove and you turn off the burner, you stick your finger in the water, it's still hot. And it stays hot for a long time. If anybody's made hummingbird food, you know how frustrating this is, because you boil the water, you dissolve the sugar, and then it takes forever to cool down enough that you can actually put it into the feeder. This is Earth's atmospheric scenario, right? So we are retaining heat on Earth that's going to stay with us for a while. And so even if we did this unlikely reforestation, afforestation change, and everybody cooperated, we're still going to be in the devastating range as of about 20, maybe 55. We won't go quite as high into it, and we'll peak and drop back down, but we have to do more, basically, than this little scenario that I've suggested, okay? If we magically peaked emissions last year, and everything in 2023 is less emission than the year before, we could very quickly see a change in the greenhouse gas concentrations, and we could also change from this high risk range. We barely enter into it and then we drop back out of it. But that's again peaking emissions last year. Global population is still growing. Regulations are still not forthcoming. We're still in negotiating stage on a lot of the agreements. As soon as gas prices go up at the fuel pump, there's hue and cry, and then all the legislation that was aiming towards getting us off of fossil fuels kind of gets tucked to the side, and we open up reserves of greenhouse gas emitting fossil fuels, and we lower the prices by letting people have their access to their gas again at the low price they were used to. So, these economic scenarios are acting against the climate scenario in this sense. It's a very hard thing to tell somebody who can't afford their fuel heating bill in the winter that they should be thinking 3 decades ahead to when we are in a devastating scenario. And so negotiations around this are very complex, and basically we need time. We need to somehow get to a point where we can work towards other solutions at the same time that we're working towards that greenhouse gas solution. So this is a cartoon that I really like. It talks about people's ability to handle news that's scary and depressing, and their tendency to just bail out of the whole issue and go on with their life as usual, because we can get away with it right now. We can still, all of us can still pretty much get away with going around our lives as usual, pretending that there's not a big looming problem in the background. But this is showing that, the disaster and the disruption that COVID created, which now that we're kind of in a much more relaxed area, feels maybe less scary than it did while we were in it. That is still, it's being followed by the economic global recession that's driving a lot of decisions right now. And then behind that is this whole looming issue of climate change. So it's like a whole bunch of tidal waves coming, and it can be hugely overwhelming. But it's important to know that these issues are there, and to know where your risks are and where your power is. And the thing that I like is that, if we had time, we can solve all of these. So we just need to work on ways for slowing down these kinds of scenarios. If we flatten these curves a little bit, if we use less fuel now, if we save a little bit on how much energy we extract from the ground, it's going to mean that energy is there longer, but it's also not all going to be dumping in at once, okay? So slowing the pace of global climate change, that is the main part of this initiative that I'm part of, that I really felt by the time that Dr. Tao approached me was the best path forward, at least for me. We have a greenhouse or climate change community group in our town, and I attended many of those meetings, and then I got very discouraged because the direction that a lot of the group wanted to go was highly political. They wanted to go and lobby at the State House. They wanted to force the state government to make changes in the regulations that would, add a carbon tax or do this or do that. And state legislatures anywhere don't like being told what to do. But in New England, I think, there's a particular stubbornness towards change, a reluctance to do anything too radical, okay? And so I've been, in this climate change game since the 1990s. It's been 33 years for me of waiting to see what kind of solutions might come on greenhouse gas control fronts. And I just got really frustrated and discouraged and decided, I'm not going to lobby when I don't see any change. But if I can do something else, I will. So the idea of this other solution is that you don't have to get agreement for greenhouse gas emissions, because what you're doing is you're taking the light coming from the sun and you're reducing the amount of it that's actually absorbed on Earth. you're reflecting more of it away. You're increasing Earth's shine to space, not dramatically, not 100% by any means. If we even manage like a half of 1%, I think that might be too much. The change in reflectivity of the Earth is what drives our ice ages. It's what causes us to have ice ages and then come out of ice ages, is that change in reflectivity and the amount of sunlight being absorbed by Earth. That is the driving factor in what causes our ice ages. So it doesn't take much leverage to cool or warm the Earth a little bit. Yeah?
So you mentioned 1%, or half of 1% would be exit. How much reflectivity have we lost because of the melting of the ice caps?
Oh, that's an excellent question. And I know that some of the climate modelers are taking that into account, but we don't have really good data on what the reflectivity was before, in large part because this, the middle of it, like Antarctica or the middle of the Arctic Ocean, is a hard place to have monitoring equipment that runs all the time. Okay, so they have a general idea, and satellites have enormously helped our data set because they're not prone to those ground-based problems. But we're probably underestimating the reflectivity loss. We know that when you go from sea ice that is like 2 yards thick, 6 feet thick, to something that's only 3 feet thick, light starts penetrating through that and getting absorbed by the ocean below instead of being reflected away. And we know that fresh snowfall like we have right now, while it's very bright and fresh, is at its most reflective, but as it ages, as dust gets on it, as soot gets on it, as leaves fall on it, it loses its reflectivity. And so, you know, the Earth's reflectivity is changing a lot all the time, but yeah, the loss of the, what we call the cryosphere, the icy world, is a big concern for this. So part of what I'm hoping mirrors can do is help recover some of that reflectivity. This diagram on the left is showing you what we call Earth's energy balance. It is just a cartoon showing that light coming in from incoming shortwave radiation. So if we look at the big fat arrow up here at the top, coming down, that's all the light that reaches the top of our atmosphere from the sun. And another thing, you know, the farther away you get from the sun, the less light is coming, because it's like if you shine a flashlight, you get the most intense light if you put your hand right in front of the beam. But if you go 10 feet away and put your light out, that light has dispersed over a big sphere, and so you get less on any one point. And it's the same thing with the sun. The farther away from the sun you are, the less light you receive, because you're sharing it with the rest of the solar system. So as we go around our orbit, when we're closest to the sun, we're getting the most intensity of light. And when we're farthest away, we're getting less intensity of light. But we also have the Earth's axis, the north-south axis, isn't straight up and down relative to the sun, it's tilted. And what's very interesting right now is that we're closest to the sun when the northern hemisphere is sort of tilted away. But we still have winter, and the northern hemisphere is cold at that time. So it's not actually proximity to the sun that's doing it. It's angling to the sun or angling away from the sun. And that's why this reflectivity is important, because you're facing the source of the light or you're facing away from the source of the light when you go from the northern hemisphere to the southern hemisphere at any given time of year. Okay, southern hemisphere is having summer right now because that side of the axis is facing the sun, okay? So anyway, you've got this big fat arrow of incoming radiation or light. Most of it's light, okay? Some of it is ultraviolet, some of it is infrared, very little is infrared. Most of it is visible light. It's in those wavelengths that we see. And the reason we see it is because our eyes were adapted to make use of the most abundant wavelengths of light, so it just got nicknamed visible light. And that doesn't change much from year to year, day to day, a little bit, but not a lot. So, the sun is coming in and it's passing through the atmosphere. Clouds, which are highly reflective, reflect some of it away, and we see that in this arrow here that gets reflected. And stuff that gets reflected back to a higher altitude, it ends up going back out to outer space. It doesn't stay in the atmosphere, it's gone. That light and that energy is just gone. The part that gets through the atmosphere and reaches the Earth and doesn't get reflected gets absorbed. And light, visible light that gets absorbed, most of that then translates into what we call infrared, and the nickname for that is heat. So light only becomes heat once it's absorbed by some surface, any surface. And a light surface, if you go outside wearing white clothes, you're going to absorb less than if you go outside wearing dark clothes. If you're in a white-colored car in the summertime, you're going to stay cooler than if you're in a black car in the summertime. Okay? This is the basic principle. So, but some of that comes through the atmosphere gets reflected away, and again, that goes out. So this is the energy balance that was part of the whole mirror logo idea, the rebalancing of Earth's energy. It's changing the amount of light that gets absorbed versus light reflected. And I think that the big issue here is that greenhouse gases do not interact with visible light. It has to be infrared. Okay, there's a lot of holes in our atmosphere for letting visible light back out. But once it's converted into infrared energy or heat, then a lot of the molecules that are in our atmosphere, not just CO2 and methane, but also water vapor. Water vapor is a very good absorber of infrared, which is why we cook with it. But also a lot of pollutants, nitrates, things called CFCs, which were refrigerants that were destroying the ozone hole for a while there until we got some of that corrected. There's a lot of things that contribute to greenhouse gases, and the more greenhouse gases we put out there, the more heat it absorbs, and then it keeps it in the atmosphere near the Earth, and it translates that heat back and forth between the ground and the atmosphere and the ground and the atmosphere, and it just warms all of the stations that are absorbing, that are recording temperature around the world, okay? Not everything's uniform. Some places, that warming effect is happening faster than others. New England is warming faster than anywhere in the continental US, with the exception of Alaska. And I'm not quite sure why, but a lot of that warming is happening in the winter. So the difference in that mean annual temperature in the wintertime has changed more than the mean annual summer temperature difference in New England. So it's really hurting our economics, our bottom line, when it's tourism-based or winter snow-based. When I was driving over here, I was listening to a PBS report about, a public radio report about logging, and how the fact that the ground has not frozen yet is really interfering with the logging season, because by now the ground should be hard enough for those trucks to get in there and get the timber and do the harvesting and get it back out to market. There's a very short window when loggers can actually do that, and that has become a lot narrower this year because, as of last week, the ground was still very soft. I don't know, a few days ago we had temperatures about 45 degrees in Plymouth. It's probably pretty warm here.
I went hiking yesterday and my foot fell through the dirt, so yeah.
Yeah. Yeah, the lakes are not safe, many of them. Rivers are not freezing over. So, these are what New England is likely to experience for climate change. So, one way of thinking about global warming and solutions to it is dividing it into two. One is that we're going to control greenhouse gases. We're going to prevent, we're going to reduce the amount of emissions that are interacting with this heat energy on Earth by switching to solar, switching to wind, things that don't emit greenhouse gases. We're going to use less energy. But in order to do that, which is the box on the right, and we do need to do it, you need the cooperation of a lot of people who are not you. Okay? Every one of us can make an individual choice to do something different. But you also need all of your neighbors and your friends and your family and your politicians to also do that. And that's very hard. This is where we're stuck. This is where for the last 30 years we've been kind of stuck in this right box where getting cooperation of people to do something different than the way they've always done it is really challenging. And we will get there. There is a change in attitude. We did it about smoking, right? Used to be everybody smoked everywhere, and it was, nobody would dream that you could control anybody's, desire or ability to smoke, and now it's just sort of status quo. We did it with acid rain. Okay, acid rain was a problem. It was a big environmental problem. We dealt with it nationally and individually, and now acid rain is only a lingering problem in the soils. We did it with lead pollution when we discovered that lead from gasoline was getting onto crops and getting into water supplies and causing lead damage to people. We took the lead out of gasoline. So these things can happen, and they can happen pretty quickly once you get a big consensus. But we've had a lot of barriers with the climate consensus because climate is a slowly changing thing, and it's not as direct a link between what somebody's doing and what's causing a disaster in Madagascar, for instance. It would be a lot easier if that was the case. The threat doesn't feel as imminent to everybody all the time. So the other solution is the left one. And again, it's not an alternative solution, it's another solution that we can be doing at the same time, and that's to increase the reflectivity by increasing the amount of reflectors we have on Earth. So we have these natural reflectors, but we also, and by the way, you should give a call out to all the snowmakers at all the ski areas, because they're helping increase the reflectivity of their mountains. Even though they're using greenhouse gas emitting tools to create that snow. We'll give them a little credit. But increasing the reflectivity can, because it doesn't let those greenhouse gases absorb any energy, it can slow down things. So when we think back to those models I showed you, that particular scenario didn't allow me to increase the reflectivity of the Earth. There's another set of scenarios called En-ROADS, EN-ROADS, ROADS, that has a lot more different kinds of levers and choices you can make, and one of them is to increase the reflectivity, the albedo, we call that, of the Earth. And when you do that, you can make very fast changes with very little change in reflectivity. But it isn't easy. It's a big world, and it's hard to change the reflectivity of the world. So we're at a point where we're really just testing this idea, and that's this project. So ground-based mirrors is one of the things that I think is a feasible approach. How many of you have heard about this idea of seeding our atmosphere, or letting little reflective particles out with using rockets or things? All right, okay. So this is different than the idea of chemtrails. Chemtrails is kind of a conspiracy theory worry that is not founded in fact, but it's not too far away from that. So these ideas are probably going to be very quickly confounded, and they might actually already be mashed together in people's minds. But the idea of cloud seeding is a long-term known one. It's, to promote rain by putting little particles in the atmosphere in order to seed water droplets that can then create clouds that can then hopefully produce a rainstorm. It's an inexact science, cloud seeding, but it's the same idea. With cloud seeding, you want to create water droplets. With these reflective particles, you don't want to create water droplets or anything, you just want to scatter light. So you put something reflective, like imagine a whole bunch of mica put into the upper atmosphere. Depending on how that mica little flake is drifting through the atmosphere, it might or might not be reflecting sunlight at any one time. But you put enough of it up there and, for a temporary period of time, it could reflect light. And we know this works. We know it does because we've seen real life scenarios of when it works. When there is a volcanic eruption, a big one that gets up into the stratosphere, volcanoes emit what's called sulfur dioxide. Sulfur dioxide is just a gas. It's a stinky one that smells like rotten eggs. But the particle is reflective. And so when it gets up into the stratosphere, it creates kind of an umbrella-like shade of reflective particles that cools the Earth. And when we look at global temperature records, you can see a dip every time there's a year where there is a volcanic eruption of that size, okay? So we know in principle that this can work, and we could do it artificially. But how many emissions does it take to send that rocket up there? How much fuel does it take to drive or fly around? Plus, you're doing something that's global. You're putting something in the atmosphere that's affecting everybody, maybe with not everybody's agreement or cooperation on that. And there's a lot of concern. The Soviets were going to test, I call them the Soviets, I'm old school. Okay, the Russians were going to test this idea about a year and a half ago. They had a scientific experiment set up where they were going to, emit little nanoparticles into the upper atmosphere that were reflective. They were artificial. It was some sort of synthetic particle they were going to do. And there was so much hue and cry around the world against it because it wasn't well tested that they actually withdrew the experiment and they didn't do it. Okay. There's another type called cloud brightening, which is more ground-based, but it's, again, working with the atmosphere where you are creating clouds because clouds are more reflective. So in areas where there might not be natural clouds, you can create clouds by putting little particles into the air, like the nitrogen seeding that they used to do to create rain. This would be just to create like ground fog or coastal clouds. And they've tested that, and it does work, but it's very energy intensive again. The thing that you have to do to create that is emitting more greenhouse gases ultimately than just the natural situation. So we haven't gotten to a point where it's feasible. Pulling carbon out of the atmosphere and sequestering it in the ground is another method to try and deal with the greenhouse gases that are in the atmosphere. That's very, very complicated science. It requires engineers and a lot of money. If you're going to take carbon and you're going to bury it in the ground, or if you're going to suck carbon out of the atmosphere and somehow convert it into something else, these take big machines and a lot of investment. And it's not something that any of us are likely to be involved in. But you could put a mirror on your roof, and you've immediately done something that's very low tech. It's totally in your control. It's low cost. And if everybody on Earth did it, there's 8 billion of us, that would make a significant difference. Okay. So again, our idea is to take something that is manageable at a local level or an individual level and see what are the pitfalls of it. We don't want to suggest this to people as something to do if there are issues. And so what we're doing is we're trying to figure out, well, how much scale would it need at a local level? Like if every town did it, how big would each town's little plot of mirrors need to be? Or, if one individual did it and every individual did it, would one mirror that's a foot by foot square be enough? Or do you need to coat your entire roof? How big a scale? So these are the questions that we're dealing with right now. And yeah, we're just in that point. So
Can I ask one question?
sure,
So on the last slide, it did kind of touch on the solar panels.
yes.
Now,
So
if you're talking about mirrors, would two-way mirror also reflect the light and the infrared? Or would a solar panel topped with a two-way mirror type deal not absorb enough to be beneficial as a solar panel?
that's a very good question. When we first started this project, Dr. Tao was he's sort of at the leading edge of, you know, materials science, and he had heard that there was a material that was a mirror with little micro laser drilled holes in it that would let in light of a certain wavelength that would be useful for the solar panels, while light that wasn't particularly needed by solar panels would be reflected away. But that, it turns out, that was a theoretical technology, and they actually hadn't perfected the materials yet. So our initial set of mirrors was supposed to be that kind. And then we ended up, you know, just getting normal standard mirrors to work with. Ultimately, that would be awesome. Right now, we're dealing with the idea that solar panels work best as energy producers when they absorb as much light as possible. So they are designed to be the opposite of mirrors. And combining the two,
Doesn't work.
we haven't figured out how to make it work. I'm not going to say doesn't. Yeah.
Has anybody thought about space enough to fill that desire?
Say that again.
Blankets.
Space blankets.
Yeah,
Oh, yeah. So this is basically the idea. Yeah. Yeah, to find a material that we can use. Right now, we're testing it with mirrors, which are glass and have an aluminum layer under the glass. But anything reflective would work. And in fact, about 20 years ago, there was a big kind of global urge for people to paint their roofs white, the White Roof Initiative. And people did it, and there was, you know, scientific tests about how effective it is. The problem is that paint actually has pigments in it that are absorptive also. So it was reflecting sunlight, but it was absorbing others. And the other part of it is that a lot of roofs where this was being done were in cities where the sky is pretty dusty and dirty, and the white would very quickly get to a point of being kind of a dingy gray, and then a lot of the effectiveness was lost. So if you replace the white roof idea with a mirror idea, though, you're you know, thinking of the same thing, only with a material that may be more durable and stays reflective, highly reflective longer. A white roof might have a reflectivity of 70% of light hitting it gets reflected, whereas a mirror is like 95 to 99%, depending on how clean it is. Okay? Yeah.
So in a lot of areas in New England, you can't have solar panels because there's not enough sunlight. How would this work with the mirrors?
It would be the same problem. You need the sun to be able to reach the surface in order to reflect away the light. And so if your roof was entirely shaded by trees, putting a mirror on your roof wouldn't be that effective. But if you had a soccer field that didn't get used 9 months out of the year, and you could quickly deploy a bunch of mirrors out there, then for 9 months out of the year, it'd be reflecting light away, and then for the 3 months during the soccer season, you could take them down, and you could use it. So, you know, this is kind of a new idea for communities, and each community is going to come up with their own solutions and things that work best. But the biggest issue that we are working with is that big open areas that are natural tend to be used for haying or sports, you know, summer sports or something. And so we had Hayers say, well, I could let you use my field, but then you're going to have to pay me the cost of the income I don't get from the hay. Oh, well, we're all volunteer, and we're hoping to just test this idea. So anyway, so part of what this initiative is to reach out to the community and let people know that there are climate solutions out there that don't require engineering, and they don't require, am I talking too long? Is that a timer?
Oh, I'm sorry, that's my watch, I apologize, no.
Time to get up and stretch, everyone. Yeah, so part of the initiative of what we're doing with MIR is to just speak to groups like you and talk to our neighbors, and talk to our family, talk to our students, and get the idea out there that not all climate solutions have to be top down, and that there's a lot that we can do as individuals that's more than just being efficient in the way we live our lives, but might be an added on step that could scale out to be valuable. If only one of us in the world did it, that's not gonna make a difference. But if 10% or 5% of that 8 billion people on Earth did something like this, or if 5% of the communities on Earth did something like this, I think that would be enough to start making a noticeable difference. So we are developing lessons for schools to use. We're developing little kits that can be sent around to explore what this reflectivity idea is and what mirrors are and what the issues of using them are. A lot of it is just getting people more comfortable with the idea of being involved in the solution in a very active way, instead of just having a good mindset about it, but to actually do a little bit of something that directly links to the problem, which is the light coming in, is it getting absorbed and turning into greenhouse gas. So we have a website also. We have these lesson plans. We have a website. We have the MIR website. We also have the MIR CAP website. It's kind of dysfunctional right now. We had a student that was helping us build it, and then she graduated, darn her. And so we have to wait for the next round of students that want to do projects to come up, because I don't know how to run a website on the scale that we want. We want to be able to put our data up there from our research fields and have people be able to download that data and explore themselves. And so getting that data link onto the website has been where we're kind of stuck. But that's the plan. And the other part of the outreach is that the fields that we have created that are test fields, we have one in Plymouth and we have one in Concord, those are open for the public to visit. The one in Plymouth is kind of at a little hidden away field that you're welcome to go visit, but you'd have to know exactly where to go. The one in Concord is right on the community college campus, and it's part of their community garden, and there's a par course for Frisbee golf, weaving in and out of where our field plots are. So it's highly open and highly public, and it's meant to be that way so that people get comfortable with the idea of climate mitigation, and they don't see it as some technology and something that's being imposed on us, okay? So this is what they look like, these mirrors. So these are two students from a couple of years ago who are helping us figure out how to set them up, what the connection point between the frame and the mirror should be, what angle it needed to be at the sun, because of course over the course of the year, the sun in the summer is very high in the sky at noon, whereas this time of year it's only like 30 degrees off the horizon at noon. And so we want to capture as much of it as possible. We want our mirror face to be perpendicular to the sunlight coming in. So to keep it simple, we just drilled one hole and one face at 25 degrees, which is about the angle of the sun between May and August, okay, the brightest time of the summer. And then it becomes less effective later. Some of the new mirror frames have 2 drill holes in them, so that you can actually unhook it and tilt it or tilt it more or tilt it less, depending on the season, in order to get a more effective capture. They're about 2 feet by 2 feet square. So they're a little heavy. Taking 2 of them at once might be more than some of us would want to do. Taking 3 is a lot. But one mirror, I can hold one mirror in one hand. And one mirror on its little post, I can hold that in one hand, and I can lift it and I can shift it, and it's easy to manage. So, high school students could do it. Certainly any adult could do it. And this gives you an idea of the scale of it. Over here on the right is just the team of people who's been involved. There's about 4 of us who are faculty at the university, and the rest are students, and then there's a whole cohort of volunteers out there. I don't even know everybody's name, because every time I talk to Ye, there's another group that he's managed to connect with and work with. So what we did the first year is we just set up 2 mirrors, because the supply chain issue hit our desire to set up this experiment, and we actually only had 2 mirrors for about 6 months. So we wanted to set it up in the summer of 21, but we didn't get our mirrors until November, and the ground was frozen by the time we got them. And so they just went into storage. But in the meantime, we set up the 2 demonstration mirrors that had been sent to us, and we monitored the ground underneath them. So the whole point of what we're doing is to understand the impact of the light that's been reflected away. The absence of that light is a shadow. So we have our mirrors here, which are very shiny on one side, but on the back side, it's permanent shadow. And the shadow of that mirror being there makes a dark spot on the ground that gets less light and is cooler than the spots next to it. But that shadow migrates around all day, And so what you're getting actually is a swath of ground underneath that mirrored area, where the ground is going to be a little bit cooler than something that's perpetually in the sun. And the question is, well, how many mirrors do we need? How much an area of that shadowy swath do we need in order to detect the difference caused by those mirrors? And that's the whole point of our experimental plot, is to understand, is 2 mirrors enough? Is 5 mirrors enough? Do we need 20 mirrors clustered around each other? How big a difference how much shade do we need really on the ground in order to have that patch of ground be noticeably a different temperature than a patch that's in the sun? So we set this up. We set up some temperature recorders in the soil. I think there's a little yellow patch right here. You may or may not be able to see it. That's the flag at the top of one of our data loggers. And we had one at 5 centimeters down, so about 3 or 4 inches. And then we had another one that was about a foot into the ground. So we're not just getting the surface, we're getting, buried in the soil. And so the 2 lines here, the blue line and the red line, the red line is the control field. That's where it was perpetually in the sunshine. And then the blue line is where we had 1 mirror causing a shadow. And what's exciting to us is that the mirrored site was always and consistently cooler than the site in the sun. So even just 1 mirror, or in this case 2 mirrors next to each other, was enough to create a difference in the soil temperature. And if you're trying to grow something, your soil has to be of a certain temperature in order for tomatoes to sprout and things like that. But it gets too hot, and then your cucumbers and your zucchini and other things don't like to grow. So in most places of the US anyway, where there's a growing season, the problem is too much heat and enough moisture. So the ability to maybe create a shade effect in an agricultural field is another part of what we're looking at as maybe an outcome of this project. They wouldn't be low to the ground like these are. These are only a couple feet off the ground. they would have to be at a canopy level so a tractor could get under them or something. But that's the idea. So the experiments that we're running, the left photo there, one of them says the Plymouth Field site. It's kind of a patch of hayfield here. And it's next to the Plymouth Airport. And interestingly, most people think, oh, you got mirrors next to an airport, the pilots are going to complain about that. But you get 1,000 feet into the sky, and it's like having, that flashlight next to your hand versus at the other end of the room. The light from the mirror gets so diffuse that a pilot looking down might notice a slightly shinier patch, brighter patch on the ground, but they're not going to be blinded. It's not going to be like a laser going into their eye causing the plane to crash. So the FAA was totally uninterested in the light aspects of our mirror field experiment. They were only interested in how high are they going to be off the ground. And we said, oh, no higher than waist high. And they said, do it. They were only interested in things that would obstruct their pilots from flying in that airspace. The other so that's one campus. And the other field where we're doing this, like I said, this is a community garden, this patch of kind of little boxes over here. And then there's a running path, dog walker's path, park course that follows the circumference of this field. And then the mirrors and the experiment is set up away from the single, you can see a single tree in there just above where the word field is, over here. We just had to stay far enough away from that so it didn't shadow our mirrors, yeah.
So I'm wondering, my hope is that the mirrors would actually cool the air and it wouldn't have to be the shadow that would be the cooling effect. And I'm just wondering if it's the shadow of the mirror that's doing the cooling of the earth, of the soil, why do you need the mirror? Why don't you have just shading things?
Well, that's an excellent question. And it is absolutely true that the mirror itself is not cooling the atmosphere above the mirror, but it's also not heating it. It's preventing the heating. If that mirror were not there, that light would hit the ground, that ground would heat up, and then that heated ground would heat the atmosphere.
I see.
So we're preventing heating of the ground. Everywhere there's a shadow, and whether it's a tree shadow or an awning shadow or any kind of shadow, it's heating that is not happening on that patch of ground. Now, unless it's a very reflective surface, the awning or the tree leaves, something is absorbing that sunlight and it is getting heated. So by using a mirror, you're just transferring whether that heat is being ultimately still absorbed by the earth or being reflected away.
But is there a way to test that change?
Yes, and the NHTI campus, that's what we're doing there. So the Plymouth field, I'm going to speed up a little bit because I've been talking a while. Just want to let you know what this looks like. So the Plymouth field, we're measuring the soil temperature, the soil moisture, everything's about that area of shadow or not shadow. We're measuring the amount of reflected light and the atmospheric temperature and humidity. And we have sensors to do all that. And then we're going to compare that to a control field where we have all those same instruments but no mirrors. This picture over here with all these wires, this gives you an idea of what our sensors are doing. All these cables are attached to a little temperature recorder, and then they're buried in the ground at a particular level. This is what the mirrors look like when they're set up. This is actually looking at the entire Plymouth field, and in the foreground, there's a bunch of little flags. That's a 36 by 36 foot plot of just sensors in the ground, but no mirrors. So that's our control area. And it's the southernmost end. And then the next field, again, 36 by 36, there are 25 mirrors in there, spaced evenly apart. and the same array, same setup of sensors in there as in the control field. So the sensors are on two axes, east-west and north-south. And then the field beyond that, it's also foreshortened, you can't really tell, but that field has 45 mirrors, and then there's a field behind that that has 65 mirrors, and then a field behind that that has 117 mirrors. And again, the sensors are exactly laid out in the same places within the field as in the control field. So we can look at the effect of the different numbers of mirrors on what the soil temperature is doing, okay? And the plot numbers, that's just the amount of plot that gets shaded by the mirrors. So it's actually an area of shade. I don't think I can show you this video, but if you go home and you link on this, and I think we can share this, this PDF or PowerPoint, if you link on that, you will see a drone overflight of the mirrors that lets you get a better sense that's not so foreshortened about what it looks like. It's very fun. And this is what it looks like in the winter after it's been up there for a while. So we do have, some of the mirrors are twisted sideways. We've had some rotation issues where we haven't been able to, these mirrors act like big sails, and the wind gust hits it and it twists it around in the ground. So we've tried to prevent that, but so far have not had a good solution for that. So we just spin it back every time we're out there. We've had some failures. I think a couple of these mirrors have come off because the suction cup that we use, or the suction that we use to attach it, is just suction cups, and some of the suction cups don't like the heating and cooling and changes in humidity. But most of them have stayed on. In the Plymouth field, we've had very, very good success. Most of the mirrors that we set up this summer are still up, and the rest are easy enough to repair.
So in the winter, you need to keep the snow off the mirrors?
No, because they self-slough. It's like a metal roof. And here is actually an example of that. This is the day after a 4-inch snowstorm. And you can see that, there's a little patch of grass where the snow didn't get to fall because the mirror was in the way. And then in front of each of them, there's kind of a snowdrift where the snow fell off the mirror and created, a little snow dump. And so, these seem to be pretty hardy as far as snow loading goes. It's wind that we've had the biggest issues with. Wind and, turns out, rain. So we had, the December 23, 24, wasn't an atmospheric river, but it felt like it. It was, a summertime-like rain event on top of snow. And it flooded the local rivers. The ground was also frozen. So even though we weren't in the floodplain of a river and we didn't get river flooding or creek flooding, it turns out that there was so much water that it pooled in our field and it flooded over a foot deep on top of the grass. And we didn't have our sensor boxes set up higher than a foot. And so where all the cables come out, and we have a little piece of plumber's putty in here to keep the critters from going in, it wasn't enough to prevent water from seeping in. And so we have a block of ice now surrounding our sensors and our battery from the solar panel, and we have to recover that before we can get any more data. We were out there just a couple days ago with a little generator and a hairdryer and an ice chipper to break up enough of the ice that we could detach the things that we need to dry out. But that's now in progress. So these are particular challenges that we've run into. At the NHTI field, wind has been a bigger issue, and the wind has blown the mirrors off of their suction cups, and the mirrors have hit other mirrors and they've broken, and so we're having a hard time getting that field actually set up in a way that is giving us good data, and that's been frustrating in particular. But the other things going on there, to talk to about your mirror thing, is we're testing clear glass So what if the structure is there, but there's no reflectivity and it's just letting all the light through? So we have a field that's shown here under clear glass, showing you how, and the sensors are underneath it, showing you what the soil effect is of just having light pass through glass. And then we have black glass, so you have something that operates more like a solar panel, where it's absorbing as much as possible. And what is the effect of the soil temperature under something that's absorbing, about 3 feet off the ground? It's absorbing the heat and it's blocking the light from getting to the soil, so it's still creating shadow. But now, it's kind of a mimic of a solar panel. What if you put up a solar panel array, and what's the cooling effect on the temperature of the shadow of the solar panel? So the black glass is meant to do that. And then we also have in this same setup mirrors. So the NHTI field in Concord, once we solve the wind problem, which might require putting up wind fencing, avalanche fencing, something to disrupt the field, because it's a big wide open field. Once we do that, it'll be giving us a lot more information about what exactly is working. Is it the mirror part that's working, or is it just the structure creating a shadow that's the most important part? I think this is a fundamental question, even about the impact of solar arrays, and how much do we have to do to try and create a reflective surface versus an absorption one. This is just to give you some very quick data from the NHTI field before they lost all their mirrors, which was sometime here in December. There was one sensor, this yellow one, that was it probably was not buried deep enough in the soil, so it was seeing much more of the day-night temperature cycle. But the others, there's 18 temperature sensors in here. And you really only see like 1 or 2 lines, and they all are behaving pretty much the same. So within the field, you are pretty much seeing, if there's mirrors there at all, they're responding the same to the daily cycle. This was the mirror field, the top one. The bottom one is the clear glass field, and it's doing the same thing, daily cycle. The only thing that you might notice is the difference between the clear glass and the mirrored glass, though, is that the amplitude of change between day and night, anywhere along here, is a little bit larger under the clear glass. So the mirror is creating a cooling of the soil by probably 2 or 3 degrees that's not happening in the clear glass field. And that's consistent whether it's in August or September with lots of light, or if it's here in November when the light levels are very low. The amplitude is still different under the clear glass versus the mirrored glass. So the mirror is having an effect. The other things that mirror is doing, and I'm wrapping this up now, is Ye Tao's organization is testing rooftop mirrors as a way of cooling buildings, so that the intensity of summer heat and the amount of air conditioning that's needed would be less. And that is being tested right now in California, but the idea is to implement field stations in South Africa and in India, where most people do not have access to air conditioning, and they may not even have fans, and they work where they live, many people, and so cooling that one space could have enormous impact on quality of life and quality of productivity. And so one of the things that they tested here is more like an aluminum kind of reflective cover. It's not quite as shiny as the mirrors. Here you see in the California one, they're reflecting the sky. That's what you're seeing. The blue there that's the sky being reflected in the mirrors, whereas here it's absorbing some, which is why it looks gray instead of sky colored. Another thing that Mirror organization is doing is thinking about, well, what if we implemented these on water? What if these were floating mirrors? where they're not, you don't have to worry about wind, you just have to worry about like waves and structure water. But the idea would be to put them maybe in fish farms so that the water temperature benefits from the cooling, and the organisms that you're trying to raise there don't have to deal with quite as much intensity of ocean warming. They're actually in the shade, which wouldn't normally naturally exist in water. You don't naturally get shaded areas unless you're near shore and you're under a ledge. They're testing, what kind of materials would it have to be? How big does it have to be? What does the flotation have to be? What's the longevity of it? You don't want this to create any contaminants in the environment. So there's a lot of students at places like Stanford and MIT and stuff that are helping Dr. Tao work on the materials science and the design of this. The last thing we're doing is we're trying to get citizen scientists involved because testing it in 2 fields in New Hampshire and a couple of rooftops isn't really giving us a good idea of how durable and practical these ideas are around the globe. So we're trying to get people in Florida where there's a hurricane season. We're trying to get people out west where there might be fires, but lots more days of sunshine. We've got people in Greece that are receiving these kits, Austria, Nova Scotia, Oregon, and California right now. But the idea is to expand this citizen science involvement so that we're getting data. And each one of these kits has the mirrors like you've seen, a slightly different type of frame where there's 2 holes where you can adjust the angle depending on your latitude and the season. And also little sensors that are cheaper than the ones that we're using, and they don't involve a lot of cabling, that can help provide data from the citizen science sites. So this is the time where I would love to take any questions that haven't been asked, if anybody's still on Zoom. If you want data until we get our website up, I'm happy to send you data. If you want a tour, I'm happy to give you tours. These are open to the public. If you want to become involved, we're always looking for people that might want to help expand the involvement, whether it's teaching this stuff in the schools or setting up mirrors on your own property or whatever. We're trying to be very community oriented and engaged in helping make this climate solution, climate mitigation idea kind of grow outward. And also the last thing is, I think it's an area for hope. There's so much bad news out there and it's hard to know what to do. This kind of idea brings the action out of the politics and to, an individual's decision or a town's decision or a small group's decision to do this. Thank you very much.
Thank you.
I'm going to stop sharing so that maybe we can see who's here. Yeah, so if there's any questions, did any come in the chat?
I was not able to go in the chat.
Okay, all right, so there wouldn't be any harm for each of us to put up mirrors on our property and spread the word. Also, any concern about our reflected light blinding pilots or incinerating overhead birds? Yeah, so I think I might have answered that a little bit. Birds are something I did worry about. I do worry about a little bit. We don't know if they see their reflection or they see what looks like a bird down there. Are they going to fly down and land on it? That's another thing definitely to think about. We haven't seen that. We used to have turkeys in the field where we were setting up the mirrors, and I think they kind of got annoyed, I don't know, by the amount of mirrors where there used to be grass that they ate. We've had a bear in the field. He hasn't bothered our mirrors so far. Really, the wind is our only enemy for the mirrors, and we haven't seen any negative effects yet. The mice love to make little nests under our control boxes, and we hope they don't chew our wires. But the idea of the materials that we chose were designed to be sustainable and durable and locally available. So it doesn't require any high tech. You can use any mirror. You go to your local store, buy something cheap. The important thing is, it's fragile. And if it breaks, then you're going to have glass, around. So the idea is to prevent it from breaking by making a sturdy enough structure. You can lay it flat. We happen to set ours up on posts just because we need to measure the temperature. We're doing an experiment. But if you're doing this on your own, you don't need to collect data. You could just put a mirror out. But you do not want to direct it at a building. You want it to direct it at the sky, because a little bit like with a magnifying glass, it is possible to reflect light on another object. And if you have parabolic mirrors or something, if they're aimed at one place, you could intensify the heat there. So aim them at the sky and everything should be fine. Are there more questions? Let's see, I would love to put up mirrors on my property. I'm thinking on the leach field. Yep. So supplies, where'd that go? I would say if you want to just set them on the ground, you could just set them on the ground. If you want to set them up above, you could build a little frame, like a lattice or something, and attach them to that. You could attach them to the top of a bird feeder, or a bird bath, that kind of thing. We created a little wooden block that we drilled holes in, and then we had to attach that to the mirror with suction cups. But there's a lot of easier ways of doing it than the way our experiment ended up falling out. Let's see. Yes, you can get the slide deck. We'll make that available. Reinmar, just send me an email. I'll put my email in the chat. Let's see.
So, Anne, the recording will be posted on the Rockingham Library website?
We'll have to check with our tech person. Probably, yeah, that's probably what will happen.
And the slide deck, or that can also be on the website, or we have to figure out a different way to get that?
Well, I think the slide deck is just a portion of what she's speaking about, right?
Yeah.
So maybe it would be good to just keep the portion where she's speaking.
Okay. Thank you.
Yeah, now, when we save this, we have the email addresses of those folks too. I can send those out, but I'm not sure. No,
We don't.
We don't have.
We don't have.
Okay, so put them on, yeah, we'll definitely put them on the website.
Okay. It doesn't look like there's questions on Zoom, but yeah, John.
I really like the idea of getting this information to schools. And are you imagining like high schools and even elementary schools?
I think
you're looking at college level.
Oh, no, definitely K through 12. And it depends on the materials that the teacher, I wouldn't recommend giving anybody, say, under the age of high school, a glass mirror to play around with on a regular basis.
Right.
But there are non-breakable mirrors that you can buy, and we actually have education mirrors that are lighter and have sort of a plastic coating on them that we can send around. And we have some sort of guided instructions. So it's like, well, what could you do with these mirrors? What could students learn from them? And a lot of them are principles of physics, principles of light, and understanding about the sun and the sun's relationship to light and to heat and the difference between those. So very, very basic ideas about science that you can experiment with. At the same time, you're learning about the role of solar energy and climate. At the higher level, high school or college, we have a lot of teachers have these vernier tools that they can use to measure temperature. So we have instruction about, you can set it up, and then you can take these measurements above the mirror in the sun. You can change the angle. You can measure the light coming off mirror. So there's a lot of things that teachers can do if they have some of the equipment that they typically have for the school. So if you know of a school that's interested, we do have that up on our website, and I'm also published an article that's going to be coming out in February that goes to a lot of schools with this idea, but happy to supply the educational material. This whole idea is that it's open. All the information's open, free. Anybody can access it. We're not trying to create any barriers. And the data is open. The only thing we can't do for free is to give away things that we've bought and then have to pay for shipping of. But we try to keep this as low cost as possible. Yeah.
Based on your model of temperature change, how many mirrors are going to be necessary to have a significant impact?
If we were going to try to get rid of the 2 degrees projected warming, it would take like 1 trillion mirrors. But to have, like to say, offset the last 5 years of warming, it might take 100th or 1,000th of that amount. That scaling issue is something we're still trying to discover. But like I said, the Earth is very sensitive to changes in its reflectivity in terms of how it responds in climate. Yes?
I have a second question.
Yeah.
Science is infamous for unintended consequences. Do you have any concerns in that area?
That's one of the things I like about this project is if this is all set up as individual mirrors and it turns out, oh, we've just had a volcanic event that's created cooling this year, we don't actually need intensified cooling, you just go out there and flip your mirror over or take it down. If it's something you're injecting into the atmosphere, it's there, you can't remove it. But if it's ground-based and it doesn't take an engineering degree to manage, that can be handled quickly and easily. So less consequences, not zero, but less, and in the control of people. Yeah.
Do you think it's more critical to choose certain areas of the Earth, like the poles, to concentrate the mirrors in, or you don't think that's going to make that much difference?
Personally, I think it's going to make a lot of difference, but we don't. That's why we want to get a distribution of citizen scientists at these different latitudes, because we don't have a good gut sense. Initially, most people would think, okay, summertime, around the solstice, when the sunlight is brightest, is when you're going to see the biggest impact. And that might be true, but let's say you have an area that's normally snow-covered up in Canada, and it's lost its snow cover, and you put up these mirrors, you've just made a big difference in that ground area. And so, and the heating that's happening, the global warming that's happening is most intense, like I said, in like New England, but especially in the Arctic. So the Arctic is warming at a faster pace than anywhere else in the world. So maybe putting mirrors up in the Arctic would offset some of that. I don't know. It's part of what we're trying to investigate, but it's a very good question.
Because on the opposite side of that, maybe putting them in the tropics would cool the oceans enough that the Arctics would create their own reflectivity again.
Right, yes. So if you didn't hear that, the idea was, well, maybe if you do it in the tropics, you could cool the ocean enough that the polar regions would start to cool themselves. They'd start to refreeze. And yeah, there's a lot of connections in the climate system that once you start a change in one direction, there might be other feedbacks on there that build on it and amplify that effect. What we really would love to do is slow down the pace of ice loss. And, in the Arctic, that's mostly in the Arctic Ocean, the sea ice is being lost because the oceans are warming underneath. And changing that trend is going to be really hard. But changing the ice loss off of Greenland or off of Antarctica is primarily we need to have more snow landing than melts every year. And that's just a difference of 0.5 degree of temperature, right? So it doesn't take very much to go from a snowy field to a, like the rain-snow transition, right? We're all very sensitive to that now. Is it gonna snow all day, or is it gonna change over to sleet or freezing rain or just rain? 0.5 degree of temperature is all that takes. So we don't need to create big changes, we just need to create small changes, but we do need to figure out where the best place for those changes are. All right, I've kept you, I'm sure, longer than you thought, but thank you very much for listening, and I have put my email in the chat, and I'm happy to answer any questions, send the slides. The video has been recorded, so I hope you'll send me a link to the recording and I can share that. Yeah. Thank you all.
Thank you.
I have to remember to save the chat. Okay. I've saved the chat. I'm going to end this.